Hello again, this is the course of data structure and algorithms, and we are going to continue our course which is related to the recursion. We already learned about the recursion patterns and the linear recursion, and today we are going to learn more about the variance of the recursion. So last time we already learned about the how to use the power and how to use the recursive squaring. Okay, yeah, you all can take a look on the previous videos, and today let's discuss about the recursion variance. For the recursion variance, there are uh, three types. Okay, so the three types are the tail recursion, binary recursion methods, and multiple recursion. So what are they? We can check this one. First, about the tail recursion. The tail recursions occur when a linearly recursive method makes its recursive call as its last step. The array reversal method is an example. So if you still remember, here let me open the previous one. So we already have the reverse. Okay. So I will give you this Jupyter notebook file. So we have this one before the reverse. Okay, so we want to swap the data. Okay, let's say if you still remember, we have this data, and then I want to swap the data with this method. So I want to swap with the reverse. So yeah, it's swap like this one. So this kind of swap happens in the iterative reverse array. Yeah. Actually, we can do with the we can do with the recursion like this one reverse, but in the tail recursion, it is also possible if we just use non-recursive methods. What is non-recursive methods? So you don't need to use the recursive methods in order to swap. If you understand the concept of the swapping, okay, so you want to swap only the AI and AJ. So if AI has been swapped into the index J, then let's make the I plus plus or I equals to I plus 1, and then let's make J minus minus, and you can say that J equals to J minus 1. So instead of making the reverse with this recursive, then we can just change with the tail version like this one. Okay, so the tail recursion is a method that you can convert into non-recursive methods. Okay, if you want to use the recursive, that's fine. But if you use the non-recursive methods, it saves more resources. Okay, for example, if in the factorial, okay, in the factorial, can you change the factorial into the non-recursive methods? That's possible. Okay, that's possible. So you don't need to use recursive. You can just use for loop. It's the same with this iterative reverse array. You can use the non-recursive method for this problem. The next one is about the recursive binary recursion method. Okay, so this binary recursion method, actually, this is another type of the binary method. In the first example, we learn about the binary search, and this one is about the binary recursion. It occurs whenever there are two recursive calls for each non-base case. Yeah. So this is the underlying principle. So we are using the two recursive calls. Okay, what does it mean? So if I have the binary sum, this is one of the method, and I have the input, which is array A, and then integer I and n. Yeah. So the output will be the sum of the n integers. So n, it means the number of integers, and the A is the list or this kind of array starting at index I. And if n equals to 1, then it will be returning the A index I. If not, then it will keep continuing with the binary sum. So this is the representation. Okay. So the 0 means the index, and then 8 is the n. N is the number or the number of integers that you have. For example, okay. For example, you have like this one, 0, 1, 2, 3, 4, 5, 6, 7, 8. Maybe this is not example, so it should be until 7, okay, because we have only 8. Okay, so if you have this 0 is the index I, and then a is 8 is the number of integer, so you will change into, you will make two branches. The first branches, the first branch is to start the binary sum from index 0 until the next 4 integer. Okay, the next 4 integer. And then for this one, is also the same. We are going to start at the index I. Okay, the index I plus n divided by 2. Okay, what is n? N is 8. Okay, n is 8 for the first time. So it is the I because I is starting from 0, then 0 plus 4. Okay, and then we have n divided by 2, so it means 8 divided by 2 is 4. Okay, then we have 4. For the first 4 is the starting index, and the next 4 is the next 4 integers after the index 4. Okay, then yeah, we will again split into 2. So because we are binary is splitting into 2. If we are splitting into 2, then we also to have the same idea. We start from index 0 and let's do with the next two integers. We are starting at index 2 and we are doing the process with the next two integers. Okay. This one is also the same. We are doing the process from the index 4 and the next two integers. So we are doing the process from the index 6 and we are going to do the process with the next two integers. Okay. So there's the common, and then yeah, you can have like this one. Okay, this is the correct example. Okay. So let's say we have 8 integers. It is the kind of list and it starts from index 0 until index 7. And if we have this one, then we can split into two. First, the first is we want to check the index 0, 1, 2, 3. Okay, this one. So the first branch is the numbers from index 0 and 4 integers. Okay, so 1, 2, 3, 4. Okay, and this one also, this is the index 4, this index 4, and then we have 4 integers, 1, 2, 3, 4. Okay, there are 4 integers. And if we want to split more, then we will split more like this one. We are starting at index 0, and then we want to get two integers. Okay, so there are two integers, and this one we are to get from the index 2, and then we want to get two integers. Okay, and so on. For the right section is also the same one. And what about the next? So the next also we want to split into the details or the leaf of the binary method. Yeah, this one is from the index 0, and then we have the only one number. Yeah, we want to start from the index 1 and we have only one integer number, and so on. Okay, so those will represent the last node because it is remaining only one, then yeah, it will return the value itself. And after we have those one, then we will get the result. We will recursive go to the upper state, and then we will go to the upper state and we will do the summation. And after we have this one also, okay, we have also this one, we go to the upper state, and then finally we will go to the first to get the final result. Okay, so if you want to take a look the details, okay, if you want to take a look on the details, you can check this one. Okay, I already give you one link. So if you want to check, actually this is a link in the given by one university. This is example in the course of data structure in CMU, is Carnegie Mellon University, and you can check the details one by one based on the yeah, this is based on the steps. Okay, so if you have the list 2, 3, 5, 7, 11, and then you can try, and then you can check right this one which step that has been assigned, and then yeah, you can go to the next to find the result. Okay, so yeah, I will let you do this one. Okay. Okay, then the next is about the Fibonacci. Okay, uh, if you already did the computer programming course, I guess you already know what is Fibonacci. So the Fibonacci number is a kind of recursive, and we can also do with the recursive methods. And there is also another way to do with the Fibonacci number, but most of people say that using recursive is good way. Then let's see. If you are using the binary Fibonacci, you can have the input which is non-negative integer. Okay, non-negative integer means it is a positive integer. So if it is a positive integer, actually it is a number from 1. But if it is non-negative, then it will include 0. So we have the non-negative integer, and the output is a k Fibonacci number. If the k equals to 1, then we return k. If not, then we will do the binary fib k minus 1 plus binary fib k minus 2. Okay, so we have I minus 1 plus I minus 2. Okay, because we know that if in the Fibonacci is a kind of a sequence. Okay, if you have the sequence 1 and then 1 and then we have 2, how can we get 2? It is 1 plus 1. And then if you have the next sequence, which is 3, what is 3? 3 is the result of I minus 1 plus I minus 2. So 3 is the result of 2 plus 1. Okay, then we can have the next sequence is 5. How can we get 5? 5 is the result of 3 plus 2. Okay, and so on. So using this one, we can use this recursive method, binary fib k minus 1 plus binary fib k minus 2. Okay. However, yeah, if you want to check the code, I also give you the code here. But if you want to do this recursive code with the binary fib, there's also another issue, which is about the computational time. If it is n0 and n1, it means if it's only the first number, okay, if the first number which is 1 and this is 1, then there is no issue. The computational time is still the same. But if it is already in the n2, so what is n2? In the n2, it means we want to do the recursive. So we will do the n1 plus n0 plus 1. Okay, so we are going to check how to get this one, and then how can we get this one. And I want to get the number, and then yeah, I want to get 1 plus 1 and plus 1. It is the result of 2. Okay, this is the result of 2, and then I want to plus with 1. And then next I want to get the number 3. Okay, it means the number 5 here. So if it is number 5, I want to get the n2 plus n1 plus 1. Okay, how can I get this one? So this is the result of the n minus 1, which is 3. Okay, after I have this 3, I want to add the 1 plus 1 in order to check with the number 2. Okay, and then what about the next? If I have this next, okay, yeah, if you want to go to next, then yeah, you will just keep continuing. Okay, and yeah, the way this is not the result. Okay, so this is not the result like you already saw for this one. For example, this is 5, then this is not 5. No, this is the number of computational time. Okay, and if you have the next number, which is 8, okay, it means we want to consider the 5 times to get this entry. Okay, because we have 1, 2, 3, 4, 5. So there are 5 operations. And then what about the n2? In n2 we have 3 operations. Okay, 1, 2, 3, and then we have the last one, which is the last one in order to get the result 8. So the operation to get the result 8, which is only 1, then it contains 9 operations. How about if we have the n5? Okay, if we have the n5, it means we want to get the next number, which is 13. So if we want to get the number 13, we will do something like 15 operations. If we do with the next number, we will do like 25 operations. If we do for the next number 41, and then the next number is 67. So using this kind of analysis, we can get that the NK will be like double. You can see 3 go to 5. Yeah, it's almost double. 5 equals to 9. So yeah, it's almost double. 9 going to 15, it's almost double. It's going to this one, it was almost double. Almost double. Yeah. And we can say it is approximately. Approximately. What is approximately? We can say in Korean is 대충. Okay. So it's around double. Then the result will be like 2 power of k divided by 2. It is exponential. So it's very heavy to calculate with the binary fib. Then is there any alternative? Okay. Because it is too heavy. So why you use this method? Okay. Yeah, we can use this method. Okay. This is one of the multiple recursion. Okay. So I can say that it's not always true that recursion can give you a better operation. It's not true that recursion can give efficient operation. Okay, then yeah, using binary recursion does not guarantee to get a better function. Please remember this one. So the alternative to make a better Fibonacci, yeah, this is another way. So you can just make a linear Fibonacci. What is linear Fibonacci? Then you can just try to calculate the next number based on the previous number. So you don't need to make a binary Fibonacci. Sorry, you don't need to make a binary recursion. Just make a linear recursion. Okay, so linear recursion is enough for Fibonacci algorithm in order to make the efficient operation. So this is the algorithm. Okay. So in this case, yeah, we have the Fibonacci numbers like this one, and then we have the k equals to 1 and k. If k equals to 1, then we return k comma 0. If it is not k equals to 1, we will have two numbers, and the two numbers will be the result of the linear Fibonacci. Okay. So if you want to know the result, let's see the code. Okay. So in the code, yeah, I already have this one. Oh, this is the power. Oh, yeah, I updated some codes. You can take a look. Okay. I give the code about the power slow and the power fast. So you can take a look which is better. Okay? The power slow means, yeah, you just use the common power method. Okay. And if you are going to execute the faster way, then you can use the power fast method. So I give you this example. Okay. Now, oh, okay, this is the binary sum. The binary sum is the result of the binary sum that you already saw before. So this is the implementation. And yeah, you can use this binary sum, or you can use this binary sum. So I give you some examples. Okay, actually they are the same. And yeah, the result is only a bit different with the way they use the recursion. So for example, if I use this data 1, I have the value 2, 3, 4, 5, 6, 7, 9, 10. Then if I use binary sum like this one, I want to do the binary sum. I want to sum all the numbers using this recursion. And yeah, the result is 46. So you can check later. Yeah, 2 plus 3 for 4 plus 5. The result is 46. Yeah, I also make another method for the binary sum. Here you can check. So this is the same with the things here. Okay. So I just so do the binary sum, and the result is 46. Okay. And yeah, now we have the Fibonacci. Okay. I explained to you that we have the Fibonacci with the binary recursion. Okay. So the binary recursion means we have the um, the two methods. We have the left and the right method is almost the same with the binary sum like this one. We are going to check the left branch and the right branch. Okay, so this is another method which is a good Fibonacci. In the example, I show you that the Fibonacci is using the two or the binary recursion. If we are using the good Fibonacci, we are just using the linear recursion. So by using the bad Fibonacci, you will get the same result, but it will take more time. If you use the good Fibonacci, you will get the same result, but it is more efficient. What is the meaning by efficient? Actually, the computational time is lower than the other. If you know that this one will take more operation time, why do you choose that one? Then the good Fibonacci will be enough for your operation. So this one is the same. Okay, if it is n less than equal to 1, then return n. If it is not, we will do the bad Fibonacci n minus 2, and we will do the bad Fibonacci n minus 1. Sorry, maybe the name is not that good, but I just give you the bad one, so you can distinguish which one is better and which one is worse. If you use the good Fibonacci, it means I want just to use the linear function. Okay, if I have the good Fibonacci, then just using the n minus 1, then I will give a result a and b. A and b is two numbers after you do with the good Fibonacci. So I don't print this number. Actually, you can print this number, but in order to just give the numbers, if I run this one, okay, if I run this one, even if I want to check what is the number, the Fibonacci in the position 6, okay, so you will get 8. Okay. In the good Fibonacci, I just put in all. So all means the a. There are two variables, which is a and b. So you can try with the a. Let's see this one. And you can see the result is 1, 1, 2, 3, 5, and the last one is 8. You can also do it, for example, a and b. Okay, if you want to check the sixth number, okay, in the b, actually it starts with 0, and then 1, 1, 2, 3. If it is a, because it is like 1, it starts with 0 first, 0, 1, and then 0, 1, and then 1, and 2, and then 3, and then 5, and then the last one is 8. So using this one, I just want to get the a. If you are going to get the first 6 Fibonacci number, then it will be 1, 1, 2, 3, 5, and 8. Okay. So that's the thing. And if you want to use the visualization, I give you also one slide here. If you want to use this one, let's see, I have this. This is based on the Python 6. You can type with the Python 3.6, Python 2.7, and you can also use the Python 3.6 with the Anaconda. It means when you do with this one, it is good tools to check the linearity. Okay, let's say I am making this one. Okay, you can use this one. Okay, if it's up to you. You want to open the print or you just close the print. If you want to see the visualization or you want to see the execution, this one, you can check. Now we are in the line number 1. If you click next, then you will go to the method. It calls the fib6. It means I want to know the first 6 of the Fibonacci number. And then if I go to the next, it will call the method. And then if n equals to 1, then it will return 0 and 1. If it is not, then it will show it will do the operation a b equals to fib n minus 1. And then you will see this one. Okay, now I will go to n, which is equal to 5. Okay, and then it will go checking again. Now n is not equal to 1, and we will go to the next, which is n equals to 4. So it will go until n equals to 1. And then what happened next is to get the tuple. And because n equals to 1, so we get the 0 and 1. And the result of 0 and 1 will be placed into the variable a and b. Okay, so a will be 0 and b will be 1. And then if you have already the 0 and 1, now we are going to the n equals 2. What is a n equals 2? N equals 2 is the result of the a plus b and a. Okay, then we will have the 0 plus 1, which is 1 and 1. Okay, and then we have the n equals to 3. What is n equals to 3? We have the next tuple, which is 1 and 1, and it will be for the next, we have 1 and 1. Okay, and then the next will be 2 plus 1, because we have the 1 and 1, and 1 and 1 will be added. 1 plus 1, it will be added, it equals to 2, and then now a is 1, so 2 and 1. After this one, we will get the same, like 2 plus 1, which is 3, and then now a becomes 2. And next, after we have the 5, 3, so yeah, that's the result. Okay, and okay, I guess this is good tool if you want to check the step by step from the your algorithm. And of course, if your algorithm is complex, you need more time to check the computational time with one by one, like the step over, like what we already did before. So the last one, I just want to explain that this recursion is one of the algorithm that you can apply. We learn about the basic definition, and we learn about the linear recursion, and we learn some recursion variants like the binary and the multiple recursion. Of course, this is one of the algorithm that is good. You can see using the binary search function, it shows a very better operation. Okay, if you use operation for the binary search with the binary, if you just use with the linear search, you will use n. But if you use binary search, you will have log n. Then it means that using the recursion, it can improve the performance. But in the Fibonacci case, it's not the case. In the binary sum, also, it's not the case. So you need to check the properties of the recursion, and especially you need to check with the iteration. Some of the recursion is good, but some of the iteration is better. Okay. The first is about the elegance. The elegance means how you can understand the code. If it is recursion, then it is easy to understand the code. So you can see we have the base case and we have the recursion. When we have the base case, we can know, okay, until they reach the base case, what happened, and then for the recursion, what happened. However, in the terms of the performance, okay, some problems can be solved efficiently using recursion, but others not. Okay, so if you are using the recursion, maybe the performance is not good in some problems, but the iteration, mostly you know that is n, is linear. Debuggability is also a kind of problem. It's difficult to debug when it comes to errors. So if you use the binary recursion for the Fibonacci, it takes a lot of time in order to check which comes to error or which come to the more complex operations. Okay. And sometimes you need to use that tools that I already explained before. Yeah, that's also one way in order to get the good operation or debug. Okay, debug, it means you want to know which is the error when you do with the recursion. Okay, I guess that's all for this video. So the chapter about recursion is now finished, and we will move to the next chapter. And I think I will finish this video, and we will do with the next chapter with other video. Okay, thank you very much for listening. See you.